Okay, welcome back to lecture 24.1, where we're going to talk about the Clausius Claperyon. How do I spell Clapeyron? Clapeyron. Equation. Okay, so the Clausius Claperyon equation is going to have to do with phase transitions, right? So last time we talked about phase transitions, and specifically we started by thinking about the conditions for thermodynamic equilibrium. Okay, that is, if I have, say, a process, when will it reach thermodynamic equilibrium? That is, when will two phases, for example, be in equilibrium. Okay, so we did this by imagining so if you remember way back to, say, lecture 1 or 2, we started saying that, temperature is that thing that's the same between things in thermodynamic equilibrium. And some of you actually had an issue with saying, oh, but equilibrium is defined as when temperatures are the constant. It's actually, equilibrium is defined when the entropy is a maximum, right? Because the third law tells us we're always going to increase our entropy as we go towards, in any process that isn't reversible, we're going to increase our entropy. If it is reversible, the entropy can be 0, so we can undo it. But in equilibrium, our entropy is going to be a maximum, or another way to say it is our relevant free energy a minimum. Right, so we looked at when volume and temperature were relevant. Right, that is, we did, for example, for a fixed volume. Then what mattered was our change in our free energy, our Helmholtz free energy was always less than or equal to 0. F was U minus TS, remember. But when our pressure and our temperature were our relevant variables, we minimized the Gibbs free energy. Right, where the Gibbs free energy was U plus PV minus TS. All right. So we expounded upon this idea of minimizing the Gibbs free energy, and we realized that at a phase transition, little g, which was big G over M, so at phase transition, this was a constant, right? Sorry, so big G was discontinuous at a phase transition. Right? Now that's what we used to define our phase transition. We saw that at a phase transition, little g was discontinuous. And so if we had like G versus T, we had two curves, and at TC, they were discontinuous. Now, remember that we had S was partial G partial T. Little s was partial little g partial t at constant p. And our little v was partial g partial p at constant t. Let me make sure I'm right about that one. Yeah. Oh, no, see, I was wrong. There's a sign. Minus. Good. Good. And so we saw that when G looked like this, S, for example, versus T, that's little s, had a discontinuity, a jump, right? We had a kink here and we had a jump. So let's say G has a kink and the first derivatives have a discontinuity. That's the better way to think about it. And we call these first order phase transitions. Okay, so that we also determined that if we have two phases, in equilibrium, for example, at a phase transition, little g1 is always equal to little g2. But that the mass between them could convert, right? That is, the molar Gibbs free energy was constant. But the masses could convert. Okay, so what we want to do today is what I want to ask is the following. So let's ask, what determines Tc? What determines the temperature in which this phase transition happens? Or another way to say it, what pressure, what is the relation between the pressure and Tc? So if we change the pressure, how does Tc change? Okay, so to answer that question, we are going to look at pressure, temperature, phase diagrams. All right. But before we look at pressure, temperature, phase diagrams, let's remind us what we mean by pressure, temperature, phase diagram. So imagine water, okay? So imagine I have a pot of water with the lid on. Let's imagine, just for now. Okay? So here's my liquid water. And I want to know, what do I mean by the pressure? Okay? So I don't mean the air, right? I don't mean the air that's above the water. I mean the water vapor. For you Canadians, I'll write it with a U. Right? We're really talking about the two different forms, the two different phases of the same molecule, right? Or the same system. Okay, so if I look, for example, at, imagine a low temperature. If I have water, for example, I have some of my molecules that come out of my water vapor, out of my liquid, and enter the water vapor. But for the most part, at low temperatures, these are going to have low energy. So they're going to recollide with the liquid and stay as a liquid. But, for example, at high temperature, you can imagine having lots of water molecules in the air, and some of them will recollide, but lots more are coming off right? So we know that, so we can already guess that at higher temperature, the pressure will be higher. And I mean the pressure, again, of the water vapor. All right, so let's imagine drawing something like that. So some pressure, temperature phase diagram. And I'm just going to pretend it's some kind of curve that I don't know what it is, okay? And that's what I'm trying to find out. I'm trying to figure out what is the shape mathematically of this curve. Okay, so let's call this the PV. This is going to be the vapor pressure, okay? I don't really, it's right, I'm just trying to accent that it's not the air pressure, it's the vapor pressure above, right? So PV is going to be our equilibrium vapor pressure. Well, we already know a couple of things. That we do know that at 100 degrees C, if at atmospheric pressure, if we have atmospheric pressure, we know that water boils at 100 degrees C. That this is the equilibrium condition. And again, I don't mean air, but I do mean that the air and the water, both vapor, are both in equilibrium. And so they're at 1 atmosphere. Okay, so we want to know how this curve depends on temperature. Okay, so let's imagine some small chunk of this, right? Oh, by the way, just as a reminder, we know that we know this to be true, but we also know that Edmonton, for example, isn't at sea level, right? So if you look back to lecture 9, I believe it was, we calculated the pressure in Edmonton. We also calculated the pressure, for example, on Everest. And so this tells us that if we vary the pressure, varying the water vapor in the air as well, will change the temperature at which water boils. All right, so let's imagine some very small chunk of this, okay? And let's zoom in really close so we can start to imagine this curve as a differential. Okay, I want to just draw some very small region where I'm going to assume that I'm so close that this is, so by the way, remember when we had this in this diagram, right, if we heat above 100 degrees, this was the vapor and this was the liquid. Okay, so I'm going to call this phase 1. This is going to be my liquid, for example, but it could be something else. And this is going to be phase 2. For example, our gas. Okay, so I'm going to imagine 2 points, point A and point B on this curve. Okay. And I'm going to imagine some delta T. And I'm going to imagine some delta P. All right? So what did we learn last time? We remember, okay, so first off, by the way, the point A is defined by the pressure at A and the temperature at A. And this is the pressure at B and the temperature at B, right? So I'm just defining those states with our relevant thermodynamic variables. All right, so this really is what we call a coexistence curve, right? So this is called the coexistence I believe, curve. It's where both of my phases are coexisting at the same time. That is, they're in equilibrium. So, what is equilibrium defined by? Well, we remember from last time we said that equilibrium would be that phase 1 is in equilibrium with phase 2 if little g1 is equal to little g2. Okay? So I can define that at both of these points. Right? I can say that little g1 at point A is equal to little g2 at point A, and little g1 at point B is equal to little g2 at point B. Right? That is, at each of these states, both of those phases, 1 and 2, are in equilibrium because the little g's, the specific Gibbs free energy are equivalent. Okay, so imagine now that we're going to move from point A to point B. Well, we can assume that there's some change in G, delta G. Because these little g1 at A and B are not equal. Okay, so let's imagine that this is a change from, what is the little change in little g? Well, let's imagine it for phase 1. That would be little g 1b minus little g 1a. Right, that phase 1 is going to move from A to B, and so the change in little g is that. But that should be equivalent for, let's call this little g1, but that should be equivalent for phase 2, right? And so we have the little g1 is actually, the change in little g, the change in our Gibbs free energy is equivalent between both phases. And for small changes, we can say that little g, so dg1 is equal to dg2. Right? The differential for the Gibbs free energy for phase 1 is the same as for phase 2. Right, and what I mean this is really for small delta P and delta T. That's what I'm really saying. Right? And so we're going to call those dP and dt also. Okay, so now at this point, let's remind ourselves what G was. So G was when T and P were the relevant issues, the relevant thermodynamic variables. we had U plus PV minus TS. And so we can just use this to say what our differential is, right? It must be V dP minus S dt, right? Because the differentials must be my relevant variables, my relevant thermodynamic variables. All right, so let's write this in terms of little g, because that's what we're really looking for. And so let's write this as little dg is little v dp minus little s dt. Right? Because v and s are my extrinsic variables and p and t are my intrinsic. Okay, so that tells us that along our coexistence curve, not only is delta G1 equal to delta G2, but we can say V1 dP minus S1 dt is equal to V2 dP minus S2 dt. Let's group those. So we're going to have V2 minus V1 dP equal to S2 minus S1 dt, or dP dt is equal to S2 minus S1 over V2 minus V1. Or let's call this delta S over delta V. All right, so now we're saying that this curve, dP dt, is defined by the change in entropy as we go along this curve, or the change in the volume. Right? Those are those jumps, delta S and delta V, that we showed last time. So one more little feature. So we know that those jumps, delta S, were related to our latent heat, right? And so we can finally write dP dt is equal to delta S delta V, or L over T delta V. And this is the Clausius Claperyon equation. And I'm actually going to make sure that you can still see that on the camera. Yeah, we're good. And this is along the coexistence curve. Right? This is, in fact, the definition of this coexistence curve. Just one note. Remember, we're using per mass or per mole. And so L is going to be our latent heat per mole. It's usually easier to deal with moles than it is to mass. Okay, so this is a very powerful equation. And so we're going to stop here with 24.1. We'll come back with 24.2, where we're going to use this Clausius Claperyon equation to define a coexistence curve.